Okay.
Cool. So yeah, welcome everyone. And this is session number 4. Am I right?
Yeah.
Yes, this is session number 4 of our 5 workshops. And today we'll be talking about applied machine learning. So without further ado, let's get started.
Okay. All right, everyone. So we're gonna consolidate a lot of what we learned in the last 3 weeks to show you some modern machine learning techniques and some real applications into literature. So all of it should come together, and everyone should start feeling okay. I just disconnected. Okay, 1 second. Sorry. Okay. Okay. So this should all consolidate, and everyone should start to feel comfortable in reviewing literature. So today we're just gonna go over some modern techniques, neural networks and convolutional neural networks, and when to use them, the strengths and limitations. And then we're going to show you some examples in literature. So, so neural networks, this is always the big elephant in the room when someone's asking you like machine learning, everyone's thinking neural networks, that's a big buzzword. So I'm going to explain it in terms of an analogy to neurons. So when we have a neuron, we have some electrical signal coming into the dendrites, right? And then, is this showing? Is what I'm drawing showing on here? I don't think so.
No, just the slide.
Yeah. Okay. Let me try to share this again.
Yeah, now I can see it. Oh,
Okay. Sorry. Okay. Okay. I, I think there's a lag between what I'm drawing and what I'm showing. Okay. Anyway, it'll appear in a bit, I think. There's an analogy between neurons and neural networks. So there's some electrical signal coming in through the dendrites into the nucleus of the neuron. And then this neuron won't allow a signal to go through until it passes some sort of threshold. Okay, now it's working, right? That's the activation threshold for it to depolarize. And once that neuron depolarizes, then it'll propagate some more electrical signal, some more electrons forward along its axon to another neuron, right? So this is a really complex building block of how our brains work. So that's the analogy that motivated neural networks. So we're gonna think of a single mathematical node. There's some input signal. So let's say this could be your data, your variables, like the age of a patient, their height, and then there's some mathematical function in the middle. We don't have to worry about what it is. It could just be a simple threshold function. Say if the input is greater than 5, then activate this neuron. And then once it's above that threshold, once this neuron's activated, then this neuron will propagate a signal to the next one. So I'll explain how this is useful. So this is what a really simple neural network looks like. So this layer, the first layer, is called the input layer. This is your input signal. Say whether the person is, let's say, from Canada or not. And the second variable is whether the person plays hockey or not, right? And then this signal will go to nodes in another layer. So all the layers in between, they're usually called hidden layers. So these are the hidden layers. And this every single node has some mathematical function where it'll sense the input from the previous nodes, and it'll compute some sort of value. So in this case, the value is actually 1, and then it'll compute some sort of output value. In this case, the output value is 0.73, right? You don't have to worry about what math function it is. Just know that there's some math function associated with it. I'll explain examples in a bit. And then it'll only activate once it's above a certain threshold and then pass the signal to the next node. And this keeps going and going and going until there's some output layer. So you see that there are also these numbers on the branches. So these are important. These are called the weights of these branches. This weighs how important the previous node is. So you can see this value is 0.8 times 1 plus 0.2 times 1, right? So in this way, all the signals earlier on will contribute to whether the final node is activated. So let's say is it this output being if this person won a Stanley Cup or not. So it'll be some number between 0 and 1. Sometimes there's a function to force it to be either 0 or 1. Sometimes it's in between, like a probability score. But the key point is that this output, let's say your prediction, is dependent on all these nodes in the back. Okay, now this is a really complex way of describing it. It seems really complex. This is sort of how our neurons in our brains work. And we know our brains are really complex at picking up patterns. which is why we start using a method like this. So in a more complex case, a neural network might look like this. So you see there are a lot of intermediate layers, a lot of different math functions in the middle trying to sense the previous input to come up with an output. So it's really good for sensing complex relationships. Let's say your clinical variables should only give you a prediction of true if they meet some sort of complex threshold in combination. A neural network would be able to predict those, but it's really hard to interpret, and perhaps we'll go over this in a bit. So to consolidate with some examples, there's the idea of a convolutional neural network, which is the exact same thing. You have these series of math functions that have an input and output with your previous math functions, but in a convolutional neural network, your input is a matrix of values. So let's say you have an image. Instead of taking a single value like the mean of the image or the height of the car or its mileage, you take the image and you take a subsection of it, whether it's a 2x2 matrix, like a square subsection of the image, or like a frame of the video, and then that subsection, that matrix, is your input to your next layer. So the reason why they call it convolutional, it's a bit of a confusing word. Convolution just means it's a certain mathematical operation. In this case, you're working with matrices. It's usually a multiplication of matrices. That's what they call a convolution. You don't have to worry about the mathematical details. Just know it's a complex way to parse through higher dimensional data. So this is a great example to consolidate it. So let's say our input is image of a dog, right? So our first layer might be mathematical functions to pick out like the maximum pixel intensity, the distribution of the pixel, whether there's, say, a gray pixel. And then our second layer will pick out the edges. So whether there's a sort of rounded edge at the end of the dog trying to represent a tail, whether there's an edge on the bottom that's curved trying to represent the stomach, right? Our third layer will do some complex combinations like thresholding, whether these combination of edges and colors meet a certain set of criteria. And then there's some, as you go deeper, you notice it gets more and more specific and more complicated. Maybe the next layer starts to look at texture. For instance, whether the texture in the middle of the image is evenly distributed, whether there's protrusions coming out trying to represent fur and everything. And then all this combines. So all this will go through, each pathway will contribute to this output, right? And depending, so let's say there are three categories. Let's say a dog, a cat, and a frog. Depending on the activations of the previous neurons, one of these categories will be activated more than the other. In this case, the neuron corresponding to the dog is fully activated. So this neural network helps use a combination of neurons to pick out specific features that are related to a dog. So the question is that, okay, what are these neurons? What are these like mathematical functions you talk about? Well, there could be simple functions, like I said, like a simple threshold. If your height is above 5, and activate this neuron and pass it on. In the case of a convolutional neural network, it's a little bit more complicated because now we're talking about a matrix of values. Let's say values like something like this, right? This would be what one neuron would look like. So visually, some example neurons look like this. So this for instance looks at sort of your middle bottom left edge and picks out pixels from there, because the pixel values there are brightly white, so it sniffs out what's in that bottom left edge. So if something there that's important, this neuron will sense it out, right? This one looks at your middle of the image. This sort of picks out the features in the middle. So you can start to see it's quite difficult to interpret neural networks, because if I was given this as a set of neurons that someone's used for their neural network, I wouldn't know what they're looking at. I wouldn't know, like, if your neural network does work, what specific features is it picking up, right? So this starts to speak to the complexity of these neural networks. But we know that they work. We know that some combination of these gives us a really complicated look at some hidden relationship between these variables that allows us to predict certain tasks. So the question is that, okay, these neural networks are really complicated. They're always cited in literature. Do you always need to use neural networks? The question is not, the answer is not necessarily. You'll see in a lot of clinical papers that look at clinical variables like whether predicting cancer from the tumor size, the number of lymph nodes invaded, or the age. They don't really use neural networks a lot, right? They use a lot of support vector machines or random forest, and random forest is a really good one because it's really intuitive, or logistic regression, right? Neural networks are used a lot for images because clinical variables like age, tumor size, your height, these are easily interpreted by the human mind, right? These are like singular variable. But interpreting an image by a human mind, yeah, radiologists and radiation oncologists are really, really good at picking up patterns, but humans aren't very good at quantifying it. If we see a texture on an image, like how do you describe it? Well, it's sort of like non-homogeneous, there's sort of a gradient. See, these aren't consistent terms that are usable consistently across observers. So images are a big use of neural networks. This is an example of a random forest, which is one of the really common methods you'll see in modern machine learning techniques to try and improve on past clinical methods. Right? You try to build some decision tree. It's like a clinical flowchart guideline. You compare the variables, and you'll go down the decision tree. You go down a branch, and then that'll give you some sort of classification. Right? Here we're comparing like the skewness of the image, the entropy of the image, and then we're given some survival of the patient. Right? A random forest generates hundreds of these trees, and they optimize them, and then they average them to get like a final optimized decision tree. So now, armed with that knowledge, we'll look at some cool examples. Discard these. So the first example. So this is a paper that a lot of medical students have to analyze. So the goal of this paper, I'll go through this quick how I would analyze it. First, just read the objective. The objective of this paper is trying to predict which children are at risk of traumatic brain injuries and whether you need a CT scan when they present to the emergency room. Right? So when analyzing any sort of machine learning paper, it's important to pick out whether they use good practices or not. So here they had 42,000, an N of 42,000, which is a great number. It's a huge number. You'll get really good representation of the population if there are enough positive cases. For instance, if they had 42,000 samples, but only one with traumatic brain injury, they're not really testing whether they can sniff out traumatic brain injuries. Right? So they have 376 cases of traumatic brain injuries, which is okay. It's a very, very small percentage of it, but over 300 is still a good number depending on how many features they used. Okay. So a lot of this in the beginning is just biostats, like we're balancing the two groups, make sure everyone's randomly assorted, make sure the observers in the emergency department are blinded. So I'll skip that. The part I want to focus on is, they call this statistical analysis. Okay, so because this is the method they're used to build their model. Okay, it starts here. They said we derived the rules with binary recursive partitioning, CART Pro. So when you hear that, like, what the heck does that mean? CART Pro. So if you don't know, if you can quickly look it up, but if you don't know, CART is an algorithm to optimize a decision tree. So they're trying to build something like, let's say you look at age, and then your second variable, maybe your GCS, right? Third variable, maybe like history, and so on. And then they're trying to come up with some conclusion of whether you want CT or no CT. Right? They're trying to create some sort of clinical flowchart guideline like that. That's essentially what they mean when they say they use CART Pro 6.0. I'm not a big fan of the language. They should just said that they use a decision tree that's optimized by CART. But that's what they mean. Okay, so standard Gini splitting rules. This is also just their way of optimizing. Gini is just a way to pick out what features is important. Okay. Now, I said one of the most important parts of machine learning is making sure you don't overfit. So the words I'm looking for here is cross-validation or whether they've distributed the patients so that they're evenly split. So I think here they said they use tenfold cross-validation, okay, which is not bad. That's for that data sample size, tenfold cross-validation is a good amount of cross-validation. Okay, so far it looks okay. They have a large sample size. They're using a decision tree. They're optimizing it and they're cross-validating it. Okay, so let's look at what their final decision tree and what they did. So I'm not going to go through all the results and details and really go really deep into it. I just want to go over the big machine learning topics. Okay, so this is the distribution of data. If you're interested, you can look at this paper. It's linked in the presentation. So this is their final decision tree, right? So the first variable they look at is whether your Glasgow Coma scale is equal to 14. If it's yes, they recommend CT. If it's no, then they look at another variable, which gives you another pathway whether it recommends CT or not, right? So first of all, I don't like this format. I think it should be like, the standard tree, top-down tree format. But this is essentially what they come up with. They come up with a clinical guideline that's in the form of a decision tree that gives you some sort of classification, whether the patient needs a CT scan or not, right? So, and then I think if you look at the results, they do some comparisons with a Canadian trial, and they absolutely beat the Canadian trial out of the park. Because the Canadian trial used like logistic regression or something. So this is generally a good example of machine learning used in literature in an impactful way. This paper eventually changed guidelines, and probably in your ED rotations, you'll see this guideline used. And when you see it used, you'll know that it was developed using machine learning. Now, the second one, I think I have time for this one. Okay, this is a fun one. So this one, I'll summarize their goal really quick. They want to predict bundle branch block from ECG. Okay, they do some fancy math transformation here that's not important. Essentially, they just change the data a bit so that it's more interpretable. But we're interested in the machine learning part. So here they go. They use an ensemble of random trees for classification called random forest of trees. First of all, no one calls it random forest of trees. Everyone just calls it random forest. And then they describe the method of the random forest. And first, there are some red flags in here that you should pick up on. If they take about 2 or 3 paragraphs to describe a machine learning method, that usually is not a sign of good, succinct and concise writing. Okay, sorry, 4 paragraphs here. They even describe it that bit down here. Anyway, I want to know why you chose random forest specifically for your project, not a description of the algorithm. But these are the results. So here they have classification accuracy. This is a number of trees they generated. So in a random forest, you generate like maybe 100 trees, 100 decision trees, and then you average them. That's what number of trees means. So now, sorry, this is accuracy, and this is down here is the number of trees generated. So this is here they're not telling me whether this is their testing accuracy or if this is their training accuracy. So this is a pretty bad figure. It's also very badly scaled. Here, at least they say that, so they said they have 68 instances of bundle branch block. This number is quite low, so their sample size isn't hitting any green flags yet. Right? They use tenfold cross-validation, which is a really high number. They're splitting their data by 10. So imagine like 1/10 of it won't have a lot of positive outcomes. Right? Now, the other figure they have is the root mean square error percentage. This is not a common way to evaluate this. Usually you want to evaluate it based off your sensitivity and specificity or your dice coefficient or your performance. This doesn't really tell us how good your tree is performing in the end. So again, this is also like a bad figure. They're comparing trees, but then you've cross-validated this 10 times. But you're only giving me a single number. Like, are these error bars? Or I don't think these are error bars. I think this is just like their indicator that they chose on Microsoft Excel on what to put there, right? So overall, they don't tell me their error range. They don't tell me their testing accuracy, their validation accuracy, and their training accuracy. And they don't really comment on how appropriate it is to use these decision trees to evaluate these ECGs. So overall, this is a pretty bad paper. And if you just eyeball it, the quality of the figures, I know it sounds superficial, but when you look at the quality of the figures and the quality of the writing, it's not very high quality, right? The scaling resolution of this figure is really, really bad. And the description, there's a lot of unnecessary description. Their equations aren't labeled, they aren't centered. It looks like their equations were made in like Microsoft Paint or something. They're not using a proper text editor to make these equations, right? So, oh yeah, this is also absolutely terrible figure. Like I don't know what this is. I think this is an ECG that they plotted on MATLAB or something, and they use snipping tool to crop it out. So overall, this paper is really pretty bad. This is like maybe 2 out of 10, right? This might qualify for a student project. Okay, so I was curious. So I looked at this journal. Like, is this even a good journal at all? And you might get misled because when you look it up, the first result of the journal it says impact factor of 3.12, right? So usually anything above 10 is really good. Anything below 1 is not so great. And it's a rough score. It's not the perfect indicator, and anything in between is a toss-up. So you can see how someone who's not trained in what we taught you in this course, that you might not be able to sniff out those specific details to know that despite having a decent impact factor, this paper is a really bad paper and should absolutely not be cited by anyone. Okay, now I think I'll spend 2 minutes on the last one before I move on, hand it over to Prash. So this is a paper that uses neural networks. So they want to, looks like they want to, if I zoom in, they want to segment lesions and they want to classify it whether it's disease or not, right? So the first step is some segmentation, and then they have classification. So you don't have to know what a discriminator is, adversarial learning is. When you read this, the words segmentation and classification should clue you as to what they're trying to accomplish. You should be able to identify what tasks they're trying to use machine learning for. Now, I won't go through the details because this one's a bit complex, but this is usually a figure. Everyone tries to make one eye-catching figure in their publication, and this is the one they have, right? They have some original image, they generate some mass, they have this, what is this, like, this figure looks like a bunch of squares that are getting smaller and bigger, right? And then they have another one, a bunch of squares that are getting smaller, and then they have like they call it a discriminator, feature extraction, and then attentive model for disease grading. Okay, so when you look at this, like, what the heck does this mean? Okay, so this one, when you read the paper, they call this their convolutional neural network for segmentation. Okay, so pretend that you read it and you know this, you've seen this term. So then with what you learned in this course, you know that, hey, this is a convolutional neural network. They're taking an image and they're taking parts of those images and passing them through neurons to try and pick up something to accomplish a task. The task they're trying to accomplish here is to segment where the lesions are. Okay, so, and then afterwards, so they don't, unfortunately this figure, they don't really go into what their attentive model is, but we can at least tell, even without technical knowledge, and I don't know everything about their method, that they're using convolutional neural networks to segment a lesion and to classify it, right? So now what I'm interested in is whether they cross-validated. I think I'm sure they cross-validated, and also their results. So here, this is a results table that really is like a gold standard. So here they use area under the curve, which is a much better evaluator than just root mean square error, and they're comparing a bunch of different methods to their methods, right? These are a lot of modern methods, and they're showing that, hey, their method has the best accuracy out of all of them, right? So this overall, it's a very strong paper. I won't go too in depth into it. I think we've gone through enough for now, but you can see they've gone through all the due diligence to get these results. They've cross-validated their results. They compare to a bunch of different methods. They tell us what they're using. They give us a good explanation of their entire method. And if you read through, you can see that they're really, really diligent in making sure that all their methods are robust. So this paper was actually from the conference called CVPR. What's up here? Okay. This is the absolute, where did it say CNN segmentation? Let's see. It's somewhere down here. There's one moment. Yeah. I remember they said CNN somewhere. I'm sorry, I can't find it right now, but I'll label it in a bit. First, this is from a journal called CVPR, and this is the absolute top, one of the top conferences for machine learning, and all the state-of-the-art methods will come here. Okay, now, so these are some examples of some publications you see in literature. There's one clinically impactful one really bad one, and the last one was something that's state-of-the-art that's not in clinical practice yet, but you see them using a lot of advanced methods to get really, really high accuracy. So at this point, before I pass it on to Prash, I'll take like 3-4 minutes. Does anyone have any questions? All right, if not, I'm gonna pass it on to Prash. I'll still be monitoring the chat. If you have any questions, you can ask in the chat, and all of us can help answering it in the chat.
Awesome, thanks, Ricky. Okay, so as Ricky explained, neural networks are almost the thing everyone's thinking about when anyone mentions machine learning or artificial intelligence these days. And in particular, they're the most used machine learning technique in medicine and in general in any applied field. And the reason that is if you remember this, I think this is the wrong slide. If you remember this figure from the previous session, I showed how neural networks are often the most accurate method when it comes to a complex problem, but this is at the cost of interpretability. In addition, the reason that neural networks are so accurate is because they're quite complex, but this also makes them very sensitive to training and testing. And so today I'll mostly be explaining why that is and how that shows up and what we can do about it. So let's say you are designing a neural network for a self-driving car, and you're looking at the images that are coming in from the camera of that car, and you want to be able to classify or detect important objects in each image that the camera feed is giving you. So you want to be able to detect road signs, pedestrians, lane markers, anything like that. So you design a convolutional neural network because your input is an image, and then you want to be able to label the images based on what you see in the image. So this could be like road sign recognition. And as Ricky explained, there are a bunch of parameters in the neural network that you're trying to fit to the data, which are typically just abbreviated as W. So this is good because you can, a camera can then, a car can itself detect the speed limit and such if it has a good camera. But the problem is that neural networks are so sensitive that even small changes in the input image can cause the output of the neural network to be drastically different. So for example, this image is slightly blurred, a blurry version of the image above. And instead of guessing 20 miles per hour, it's going to 80. And similarly here, the stop sign, you can see that a few pixels are, actually these aren't even pixels, I think someone actually has put stickers on top of the stop sign to obscure it a little bit. And the neural network completely misclassifies this image. And so obviously in a safety critical application like self-driving cars, you can't have these kinds of errors because the car is going to totally fail driving like a human would. So here's another fun example. I don't know if you can tell what the difference between these two images are. Obviously it's an image of a pig, but visually to both of us, to all of us, both of these images look exactly the same, right? But when given to a state-of-the-art convolutional neural network, the image on the left is correctly classified as a pig with 91% confidence, but the image on the right is classified as an airliner for some reason with 99% confidence. So you can see that sometimes people are rightly not fully trusting of neural networks and how they're trained and their outputs. And this is the actual difference. So between the two images, there was random noise just injected. And in this particular figure, I'm showing that noise as very emphasized. So visually to humans, this difference is totally imperceptible, but to a neural network, it makes a huge difference. And similarly, even if no noise is injected, this neural network, which was trained on trained to detect different animals, when it's shown a statue or some sort of wooden carving of a turtle, it actually misclassifies these images as rifles or some other class, and none of them are correctly identified as a turtle. And so this concept of neural networks being really sensitive to the exact input that they're given is known as sort of the concept of brittleness. So neural networks are very dependent on the data that they're trained on and the sensitivity of their parameters, so that when the input image is even slightly different from what the network was originally trained on, or if it was optimized in a very poor manner, then the output can be hugely different from what you're expecting. And so can't always be trusted as a good machine learning model. So how do we overcome this? There are many mathematical and optimization tricks, but I'm going to talk about just one simple and very commonly used technique called data augmentation. So if noisy images and weird images can trick your neural network and fool it, then why don't we just train the neural network with those noisy images? So that's the basic idea behind data augmentation. So instead of just using one picture of a yellow bird in this case, without any noise, why don't we augment the image using different types of noise, different types of color shifts to train the neural network to identify all of these images as a bird instead of just the original. Similarly, let's say you're designing a neural network to identify famous landmarks around the world. Instead of just giving it one image of each landmark, or even multiple different images of landmarks, you could take each image and then transform it in many different ways. For example, rotate it, skew it, translate it, change the contrast, and so on in sort of infinite combinations to train the neural network on all of these different images. And then if you do that, the robustness of your neural network increases significantly. And so almost in all modern neural network papers, you will see some sort of data augmentation being used. And for images, this is usually pretty easy to apply. So before moving on, I'll see if there are any questions on that. Otherwise, I'll move on in a few seconds. All right, so As Ricky mentioned, neural networks are not always the answer. It totally depends on your data, how complex it is, and usually you should exhaust other options before going to neural networks. So we already mentioned some classic techniques last week, such as logistic regression, decision trees, and random forests and linear regression. And this is just an overview of how those different methods perform on different data sets. So you have three different data sets here in two classes. You've got this crescent style data set in red and blue. And then again, you've got sort of a smaller blue circle surrounded by a red donut. And then you've got two different classes here, which are linearly separable. And then these are the various most common machine learning classifiers that you can apply to these. And I'm not sure if it's clear, but down here in the bottom right, you can actually see the overall accuracy of those classification techniques. And you might notice that actually neural networks, which are all the way here on the right, aren't necessarily always the most accurate methods. So for example, here, the neural network actually classifies these two data sets, or these two classes, rather linearly instead of recognizing the crescent shapes of the data. Whereas, say, the nearest neighbors algorithm, or the SVM and the Gaussian process both identify the crescent-shaped distributions of the two classes. And then you can see clearly that with decision trees, this is also rather successful, but the classification boundaries are all based on sort of straight vertical and horizontal lines that you can draw in space. And then similar results are seen here in these two other examples. So if we have time at the end, I'll come back to this and I'll show a live demonstration of this, but hopefully most of you had a chance to click on this link last week and play around with it. So you should have found the same results as in this figure. And I'd be interested to know if what you guys found, if you did use that website and if it matched what you're expecting. So in machine learning and generally in science, when it comes to picking a method, people often refer to Occam's razor, and this is probably something you use in medicine as well. And this is just a simple rule of thumb, which says, if everything else is equal, then you should choose the explanation, which, oh, this is a typo. This should be choose the model with the simplest explanation. So for example, if your logistic regression is performing exactly the same as your neural network with the same accuracy on the same data set, then there's no reason to favor the neural network, which is a more complex model with more parameters. You should just choose the logistic regression. And this applies similarly to many other fields. For example, in medicine, if you have a patient which comes in with a set of symptoms and test results, and you have many competing diagnoses which can explain all of them, then you should try and maybe pick the simplest or the most common one, because there's no reason to pick a weird genetic abnormality over something simple like hypertension. So I'm going to also end this section with a deep dive into an applied neural network paper. And in contrast to what Ricky showed, this one is actually published in a medical journal, PLOS Medicine, which is a pretty good journal as far as I'm aware. And the reason that this was published in a medical journal as opposed to a more technical computer science or engineering paper is because the whole point of this particular paper is to show a pretty standard convolutional neural network, which was validated very thoroughly in a clinical setting, as opposed to a very new convolutional neural technique, which wasn't validated very thoroughly clinically. So in this paper, the Stanford lab develops a method called ChecksNext, which is essentially a deep learning convolutional neural network for identifying different diseases in lung x-rays. So their motivation is really simple. Of course, thousands of radiographs or even more maybe are taken every day and need to be diagnosed or read. But unfortunately, there aren't enough radiologists to do it in a timely manner. And so this becomes a time-consuming task, and usually there is a backlog of chest x-rays to be read. So why don't we just offload this to a machine? So Why don't we just use a neural network, because those are known to be very well performing. So I'm going to talk about just the things that are really relevant to what we've been discussing in these past few sessions. The paper is quite long, actually, but I'm just going to focus on the concepts that we touched on. So for example, in the method section, they do spend a long time describing the data, which is a good sign. And clearly we can see that they used a huge number of x-rays, 112,000, from the biggest open database that is known or is publicly available. And these are all frontal view x-rays. And those all came from almost 31,000 unique patients. So clearly they're using a ton of data, which is a good sign. And furthermore, they described that each of these x-rays was annotated with up to 14 different pathology labels. So each x-ray could have up to 14 different things in it, such as different nodules, and they'll explain what those are. They also provided a very helpful table which showed how they split the data. So remember from the last session, it's very important to have a separate training, validation, and test set. In this particular study, they called it training, tuning, and validation set. So in this case, the tuning set is the same thing as the validation set for when we were talking about it. And then the validation set is the same thing as the test set. So clearly you can see that their training set has the highest number of images altogether, which is expected. Their validations or their tuning set is a slightly smaller split. And then finally their test set is even smaller. But as I will explain later on, they actually use this test set and rank it against many different radiologists, not just against the algorithm itself. So the convolutional neural network itself, in this study, they use something called a dense net. Now, you don't have to worry about what that is. It's just another fancy name for a very large convolutional neural network. The reason it's dense as opposed to just a normal network is because each convolutional layer that is used in this network is connected to every single other convolutional layer. So you can see these lines showing the connections between these layers. And this is why it's called a dense net, because it's densely connected, as opposed to a more traditional or conventional convolutional neural network in which each convolutional layer is only connected to the one after it and the one before it. So the authors argued that using these extra connections has shown to help improve accuracy. So that's how they justified using this model. Now, the test set, they also went into quite a bit of detail as to what that was about and how they performed, how they clinically validated their algorithm. So they took all of the 420 images from their test set, and they actually asked 3 different radiologists to annotate it into all of the different 14 pathologies that were present in these images. So 3 different specialists did this. And they also picked the test set so that at least 50 cases of each of these 14 pathologies was included. And once again, that goes back to something Ricky was saying, that they tried to make sure that they had enough positive cases in the test set so that their final errors made sense. And they weren't just looking for like that one lung cancer in 400 images, but they had at least 50 cases of each pathology. And then, separate to those 3 radiologists, they had 6 other radiologists from 3 different institutions, as well as 3 residents, also annotate the validation set separately. And the reason for this was to essentially test the performance of these 9 radiologists against the algorithm's performance. So all radiologists did this independently. And specifically, the radiologists didn't actually have access to any other patient information. So they can use the patient's history or any other imaging to decide what the X-ray showed. And this is the same as the algorithm, because the CNN also can only look at the image. It can't look at any other information. So in a way, it's a fair test. But obviously, when you think about practical implementations, there's no reason a radiologist wouldn't look at patient history also. So this is actually one of the shortcomings of this study. And these days, more and more techniques are looking at incorporating all patient information in CNN studies and not just the image. And finally, in terms of how they evaluated performance, they looked at 6 different metrics, which is also a good sign. They instead of just reporting accuracy, as many papers do, or just root mean squared error, they made sure to show a sort of more consistent and more complete overview of the performance of both the CNN and the radiologists. So we've already talked about some of these. This is area under the curve, which is a very robust way of measuring accuracy, sensitivity and specificity, and the positive and negative predictive value. Obviously, those are all about how many cases you miss or how many cases you catch. The F1 metric is a way of combining these metrics together. And then Cohen's kappa is something you don't commonly see, but it's a way of measuring the reliability between reaches. So onto the results. They have some really nice figures in this paper. And by the way, the paper and all the supplementary materials I have linked later on in this presentation. So this is what the CNN did. It took an image like this in, and as you can see, the images had some artifacts. For example, some patients had catheters in their image. But not only did the CNN sort of output what this was, so I actually forgot what exactly, I think these are lung masses that the CNN said it was. So not only does it classify the image with the label that it thinks it should have, but it also highlights where it thinks that label information is coming from. So for example, here it's detected something here. I'm not a radiologist, so I don't really know if this is correct or not, but I think these were examples of good predictions. But apparently there are some lung masses here. And then once again, this is a different pathology. Once again, the neural network will say what pathology it'll classify the image, but it will also produce this kind of heat map, which shows where exactly or why exactly that neural network thinks this pathology exists. So this is an attempt to make the neural network a bit more interpretable. So as a radiologist, if you use this as a tool to help your diagnosis, not only do you get just a single output, but you also get a heat map which shows you how the neural network is thinking to come up with this answer, which is pretty helpful. Now, quantitatively, they also provided very good statistical analysis on how the CNN did against the radiologists. So here are the 14 different pathologies that they tested for. And in the greenish line are the performance of the radiologists. And in the blue line is the algorithm. And then in case you forgot, this straight black diagonal line is just the performance of a coin toss. So this is like just by random guessing, you would be able to get this much performance on guessing the disease. So the more close or the more concave these curves are, and the closer they are to this point here, the better they're performing. So overall, they found that the neural network beat the performance of radiologists in one of the disease classifications. The radiologists beat the neural network in 3 of them, but for the rest of the 10 diseases, they had equivalent performance. So clearly, I think in this, in emphysema and hernias, the radiologists had better performance than the neural network. I forget, I think it was in this particular case, can't really pronounce this, that the machine learning technique performed better than radiologists. So this was a very thorough analysis of the output of the neural network. And then they also broke it down by the other particular metrics that I mentioned. So here they're plotting in blue again, the algorithm performance, and then the performance of the residents and the staff radiologists. And then in orange are the average of the residents and the radiologists. So once again, it shows how exactly the algorithm performs, where it can be considered to be better or equivalent to radiologists, and where it's worse. So the reason I presented this paper is because I remember when it came out first, I think 2 or 3 years ago, it was making the rounds in AI communities. Because I think this is the first time that, even though chest X-ray diagnosis by AI had been around for a while and many papers have been published on it, this was the first time that such a method was so thoroughly validated against clinical experts to really show that AI can be actually used in clinical practice alongside radiologists' diagnosis. So was it a win for AI? You can say it wasn't, because it wasn't as accurate as radiologists on all of the diseases. But on the other hand, you can consider the other huge advantages that it had. For example, it was mostly the same as experts in many of the other categories. And given that it's so much more efficient at just analyzing an image, it can definitely make radiology much more efficient. And so this is why many times it's not true that AI or CNNs are going to replace radiologists, but rather radiologists can definitely adopt this technique to make their practice much more efficient, so they can spend more time doing something more meaningful than just reading X-ray images. Yeah, so I already talked about this, but this is an example of a very good scientific and clinical machine learning study, because clearly they had a ton of data. They explained very well how they split it into tuning and validation and testing. They had a huge number of human experts to validate this method against, which is quite remarkable, because imagine getting the time of 7 or whatever it was, 10 radiologists and going through all of these images is very difficult and time consuming. They used multiple different evaluation metrics, which is also something that you see rarely. Instead of just picking the one that makes their method look attractive, they actually use a whole host of metrics, which is a good sign. And then they also did statistical analysis between the final metric values to see if there were actually real differences in performance, or if it was just chance. So here's the link to the paper and the project page. I definitely recommend you guys check it out, read the summaries. They even made a couple of videos to demonstrate how this neural network can work on your phone, which is really cool. Yeah, so I think that pretty much brings us to the end of this session. We covered convolutional neural networks in a little bit of detail, but not too detailed. I would highly recommend, if you find it very interesting and you want to learn more about how they work, read on these two topics as well. So optimization basically explains how the neural networks actually learn their parameters and how the data is used to update these parameters with each iteration or each new set of data. And then generative adversarial networks are kind of spin-off method from convolutional neural networks, which actually are able to generate new images from a bunch of images that the network has seen, not just be able to classify them. So this is another type of model that is gaining lots of recognition in medicine. And so it's also well worth checking that out if you really want to be on top of AI methods in medicine. Yeah, so that's all for me. I'm happy to take questions for us. Yeah. And we'll have I think, forgot to mention right here, but we'll have a programming workshop, I think, in a couple of weeks. So in that, I hope you guys are looking forward to it, but essentially you'll be able to, given a data set, you'll be able to train these different machine learning algorithms that we've talked about, and you'll be able to directly see their performance and their limitations. And it should be really cool, and especially if no one here has programmed, it's really cool to be able to put into practice what you've learned over these last 4 weeks. So yeah. You're welcome. Okay, yeah, I can demo the website if people are sticking around. Let's see. So, okay, so here, let me walk through it a little bit. I already used some data from before, so I'm just going to upload it. So feel free to speak up or type in the chat I'm looking at now if something I say doesn't make sense. So essentially, here you have the option of plotting your own data set in 2 dimensions. So I've plotted this data set in orange squares and these purple squares, and the color essentially denotes their class. So the orange squares are meant to be classified differently to the purple squares. And I picked this crescent shape because these two data sets are now not linearly separable, which means you can't draw a straight line between these two data sets to separate them perfectly. And that's important to know, because if you already know that your data is not linearly separable, then you can't use certain types of algorithms. So for example, once you use this website and you plot your own data as you wish, you can then pick different machine learning algorithms that are used for classification. So in our sessions, we talked about the perceptron, which is essentially a single neuron in classic neural networks, and is the equivalent usually of logistic regression. So if you guys remember logistic regression, it's not really able to classify non-linearly separable data. So we shouldn't expect it to do very well. So once you select your method, and then you can choose how many iterations to run it for. So I'm just gonna pick the maximum, which I think is 99, just to give it the benefit of the doubt. And then you press train. It will then show the output of that particular classification method. So as we can see, the logistic regression didn't do a very good job of identifying which space sort of should belong to the purple data and which space should belong to the orange data. This is sometimes called the classification boundary or the decision boundary. And this just means that, let's say you had a new piece of data coming in and you don't know if it's orange or purple, but it falls right here, then this decision boundary would classify that as a purple square. Whereas if the new data point landed here, then it would classify it as an orange square. Now, obviously, it's not very accurate, because in this case, if a new data point came in right here, this logistic regression algorithm would classify it as orange, even though we can visually see that it should belong to the purple class. And same here, if we had a new point here, then it would be misclassified. Now, on the other hand, a very simple but usually effective algorithm is called k-nearest neighbors. So here's a question. What about a different functional form for the logistic regression? So usually the logistic regression is you don't choose the function. It is a sigmoid function, so you can't change its exact function. That is kind of how it's defined. Whereas the neural network is something where the function itself you can change as you train it, which is why neural networks are so powerful. But things like logistic and linear regression, you can't change the function, you can only change the parameters of the function. So if I retrain this, it might come up with slightly different decision boundaries. As you can see, if I'm clicking on logistic regression and just clicking train multiple times, it will come up with different decision boundaries because of the inherent randomness in how this method is trained. But the logistic function remains the same internally. And so k-nearest neighbors are usually more effective, and that just simply uses, it'll pick a point or a space on this 2D canvas, and it will look at the, in this case, I've selected k to be 3. So look at the 3 nearest points. And in this case, for example, where my cursor is, the 3 nearest points are all orange. So it's going to classify that space as being orange. So, and same for purple. So if I have my cursor here, it's going to find the 3 nearest points. Those are all purple. So it's going to say that that space belongs to purple. So if I click train, as you can see, it does a much better job of delineating this decision boundary. So now when you have a purple spot here, it will be correctly classified as well as here. Usually, the higher you make k, the more smooth your decision boundaries will be. And this is a way of avoiding overfitting. So if I make it 100, you'll notice, or depends, you might see that the decision boundary is much smoother. So I have to give it some time to train. Yeah, so you can see it's smoothed out way too much. And even though it's not a straight line, it's kind of like, it's curving a little bit, but it's now doing a much poorer job. Whereas if I make it 10, for example, it goes back to performing well. And then, so if we go the other way, 1, this is the equivalent of overfitting because it just uses information from the nearest point to decide the decision boundary. So in this case, I've made my data nice. There's no like overlap or there's no noise. So it does a good job even with just one nearest neighbor. And so you can go on and play with the rest of these. So with neural networks, just remember those different circles and the hidden layers that Ricky was showing and the connections between them. These are your two inputs, your X and Y coordinates. These are the neurons in the first hidden layer. These are the neurons in your second hidden layer, and this is your output layer. So you'll find as you train yourself that neural networks are quite sensitive. So I'm just going to go with the default settings here and hit train. It takes a bit longer to train, but eventually you'll see that the decision boundary updates, hopefully. Yeah, so as you can see, it didn't perform very well at all, which is disappointing because neural networks are meant to be so powerful and accurate. And you'll see as you play around with these parameters, you can get it to fit this data set very well. Sometimes it's just because of how random it is too. So if I click train again, it might come up with a totally different boundary. And that's why neural networks, as you can see, are very sensitive to training. So you should always use caution when training them. So that didn't really do a good job. You can try making it deeper by adding another layer and then seeing if that helps, and just play around with these techniques. So we will do exactly this same exercise in a few weeks, but with code. So you code it yourself, and you'll be able to look at some meaningful medical data from cancer tumors to be able to classify them using logistic regression, using neural networks, and using decision trees. And same thing for decision trees. You can see that it creates boundaries based on just horizontal and vertical lines. Yeah, so any questions? Did that help explain the website, or is there something that you still didn't get? This last one is decision trees. Oh, support vector machine. So support vector machine is another powerful classifier. It's quite mathematically intense, its explanation. So I'm not going to go into how it works, but essentially it takes this nonlinear data and reprojects it in a linear way in a different combination of dimensions and then classifies it. You can definitely read more about it, and there are actually some good YouTube videos that explain it a bit better than I'm explaining it. But this is also a very popular classification algorithm that's used for both linear and nonlinear data sets. So once again, you have to play around with these parameters to figure out what works, and it can be a bit sensitive, but this essentially will try and find the best decision boundary between two techniques, or sorry, two classes. And I've actually forgotten from my lectures what the parameter C means. So that's something for you to find out. Cool. If there are any more questions, feel free to type them out.
Okay. All right. So thanks everyone for coming to this session, and thanks Prash. So in 2 weeks, we'll have a program workshop, which is really cool. It'll give you a nice concrete example. Otherwise, we'll post all our updates and recordings on Slack. Thanks everyone for coming, and have a great night.
Thanks everyone.